coming to you from a hotel in Pennsylvania. Let's see. So this week in our all deep causal probabilistic programming reading group, we're reading this paper, Causes of Effects and Effects of Causes. Let me get that on the viewer here. Great. Let's see here. Meanwhile. Okay. Let's see here. Okay. So we're switching gears a little bit from what we've covered before in the reading group. Now we're moving a little bit into some of these ideas having to do with actual causality. I'm excited. I think these actual causality ideas have a lot to do with some of the more cognitive science elements of causal reasoning, and that's important, I think, because it has some impact on how we might apply causal inference algorithms to problems of artificial intelligence, particularly agent modeling and reinforcement learning. Great. So, causes of effects, effects of causes. So again, I usually try and scan through the articles at a top level, and then let's see here. Let me see if I can't pull a little side view up here. I try and go through these at a top level, and then if there are, and then kind of, take that onion. So in journalism, they have this idea where you read down a newspaper article like in the New York Times, and the first paragraph basically tells you everything you need to know from a high level, and then the second paragraph goes a little bit into more depth, and then the third into more depth, and so it's like peeling back layers of the onion. That's not how papers are designed, but I try to scan them in a way that allows one to get a very high level of what's going on first, and then kind of dive in, and time permitting or intermitting, you kind of go in further as you go. So that's what I'm going to try and do here. So starting with the abstract, this article summarizes a conceptual framework and simple mathematical methods of estimating the probability that one event was a necessary cause of another, as interpreted by lawmakers. So this legal approach to causal reasoning. This is something that Pearl talks a lot in terms of so Judea Pearl being a very kind of seminary researcher in the field of causal inference. He talks a lot about law, because that's essentially what we're trying to do in a criminal case, right? Like find out if this person's actions were the cause of the bad outcome, the crime, or if somebody is at fault, or say liable. These are all questions about why or what intentions were. These are all causal questions, and it's interesting because that these legal applications have direct connections to machine learning applications, particularly in agent modeling, because we're trying to have agents reason from a policy, and so so if an agent makes a mistake, it gets a low reward function, and it wants to reason about what caused it to get this bad outcome. We're using similar reasons that we might use in a legal setting. So let's see. I'm just going to put on a little bit of tunes here, and I'm logged out. Okay, no tunes in. All right, so this article summarizes. All right, we got that already. We show that the fusion of observation and experimental data can yield informative bounds that under circumstances meet legal criteria of causation. We further investigate the circumstances under which such bounds can emerge, and the philosophical dilemma associated with determining individual cases from statistical data. All right. Okay, so introduction, grateful to blah, blah, blah. My aim is to comment in this, is this a comment? Oh, this is, okay. My aim in this comment is to share with researchers a progress report on what has been accomplished on the question of cause and COEs, okay. How far we've come using population data to decide individual cases and how we can answer questions that lawmakers ask about an individual's liability. I hope this account convinces readers that the analysis of cause and effects has not, of causes and effects, has not lagged behind that of effects and causes. Right? Why are these two things different? Effect of causes and causes of effect. Okay, so, all right, so there's another argument. There's another paper. Okay, I thought this was all just platitudes, but no, there's another paper here that is making a distinguishing between the effect of causes and the causes of effect. And I guess he's going to kind of, this must be argued towards a sociological audience or perhaps a legal audience, and he's going to try to formalize it a bit, my guess is, without overwhelming this audience. So I hope this account convinces readers that the analysis of causes and effects, the causes of effects, has not lagged behind that of effects of causes, but both modes of reasoning enjoy a solid mathematical basis endowed with powerful tools of analysis, and researchers on both fronts now possess solid understanding of applications, identification conditions, and estimation techniques. All right, so first we're going to start. This is probably going to be easy to read through since it's going to be just a commentary. And it looks like we're, all right, theorems, that's something. A numerical example. And now he's going to look, all right, so this is actually, looks like a bit of a summary of some of the stuff in Pearl's book. Should be interesting. All right. Let's jump right to the conclusion. See what he's going to, is there a discussion section? All right, let's see what the conclusion is before we, so we'll know where we're going and then we can enjoy the journey. I agree with DFF that the issues surrounding reasoning from effects of causes to causes of effects involve the challenge of reasoning from group data to individual cases. However, the logical gulf between the two is no longer a hindrance to systematic analysis. It has been bridged by the structural semantics of counterfactuals, and now yields a coherent framework of fusing experimental and observational data to decide individual cases of all kinds. I invite DFF to reap the benefits and opportunities unleashed by the counterfactual theory of causes of effects. Unleashed. All right, let's see what's going on there. I have unleashed my causal theories. Reap the benefits of what I've unleashed. All right. The logic of counterfactuals, good place to start, is the mathematization of counterfactuals, a development that is responsible, at least partially, for legitimizing counterfactuals in scientific discourse, and which has reduced the quest for causative effects to an exercise in logic. At the center of this logic lies the model, consisting of a set of equations similar to those used by physicists, geneticists, economists, and social scientists. So he's going to talk about a structural causal model, right? So we got a bunch of equations that are going to be our causal model. Articulate scientific knowledge in respective domains. M consists of two sets of variables, U and V, and a set F of equations that determine how values are assigned to each variable, V sub I in the set V. Thus, for example, the equation small vi equals Fi, which takes arguments V and U, describes a physical process by which nature examines the current values, V and U, of all variables in V and U, accordingly assigns variable Vi the value, all right, great, small v. This the variables in U are considered exogenous, namely background conditions for which no explanatory mechanism is encoded in the model. Every instantiation U equals small u of the exogenous variables corresponds to defining a unit, in the sense what a statistician would call an experimental unit or a unit of observation, or a situation in the model, and uniquely determines the values of all variables in V. Therefore, if we assign probability Pu to U, it defines a probability function on V. So in other words, everything, so we have these endogenous and exogenous variables. U is exogenous. If we put a probability distribution on U, since the V's are all deterministically driven by U, then we actually have a probability distribution on the entire set of variables. The probabilities on U and V can best be interpreted as the proportion of the population with a particular combination of values on U and or V. Right, so that's kind of, from a frequentist standpoint, we think of those probabilities as proportions of a group of people who have. So if each one of these U's is a person, then a probability distribution on U kind of is the distribution of people who have different values, different settings of U. So each U is like the profile of an individual, and then this is the probability distribution of profiles from a kind of population statistics standpoint. The basic counterfactual entity in structural models is the sentence, Y would have been taking the value small y had x been the value small x in a situation U equals small u. Denoted y sub x given U as an argument equals small y. Where y and x are any variables in V, the key to interpreting counterfactuals is to treat the subjective phrase had x been x as an instruction to make the minimal modification to the current model so as to ensure the antecedent condition x equals x. Oh, okay. Period. Rephrase. The key to interpreting counterfactuals is to treat the subjunctive phrase had x been x as an instruction to make a minimal modification to the current models so as to ensure the antecedent condition x equals x. So what does that mean? That means, when I asked the question, what would y have been had x been something, then we're just saying, we're saying that with respect to our model, we just need to change the model as minimally as possible, such that that x is x. So and kind of incorporating the information of what we observe about. Incorporating any kind of evidence that we observe, updating that probability distribution, then going inside and changing x, that antecedent condition to understand and having that model incorporate that change after it's taken in all the available information. So these are Pearlian counterfactuals, and if you're new to them, they're actually pretty cool. I've written a few papers on them, but and they're fun to program. Writing abstractions for them in programming languages so that you can capture this idea is pretty interesting. But saying them out loud like this, I think he's being concise, but I don't. If I were a sociologist reading this, I'd probably be a little bit confused. Such a minimal modification amounts to replacing the equation for x by a constant x, which may be thought of an external intervention, do x equals x. Not necessarily by a human experimenter that imposes the condition x equals x. Replacement permits the constant x to differ from the actual value of x, which would have been set by v and u for that function x, without rendering the system of equations inconsistent and thus allowing all variables, exogenous as well as endogenous, to serve as antecedents. See, I understand intimately what this notation and everything means, but these sentences, when I read through them, I find myself a little confused. That's okay. It's hard to explain precise ideas. Letting m sub x stand for a modified version of m, with the equations of x replaced by x equals x, the formal definition of counterfactual y sub x given u reads as this. So what is this saying here? So I guess you're saying that this counterfactual is equivalent to this intervention in the model with a y under in this intervention model under a specific setting u. In other words, counterfactual y sub x given u as our argument is in model M is defined as the solution for y in the surgically modified submodel M sub x. All right, then we have, so I think it's pronounced Gales and Pearl and Halpern have given a complete axiomization of structural counterfactuals, embracing both recursive and non-recursive models. They show, and I think recursive just means that there are not in recursive in the computer science, and it just means that you have a directed graph with cycles, and non-recursive means a DAG. Well, I could be wrong about that. That's what I think. They showed that the axioms governing recursive structural counterfactuals are identical to those used in potential outcomes framework. Hence, the two systems are logically identical. A theorem in one is a theorem in the other. This means that by relying on structural models as a basis of counterfactuals does not impose additional assumptions beyond those routinely invoked by potential outcome practitioners. So potential outcomes versus structural causal models, potential outcomes is another and probably kind of practically more common way of doing causal modeling, but they're theorem equivalent approaches. So what Pearl is saying here is that you don't lose anything by using his approach, which in practical settings could be argued, but theoretically he's right. Since our model M consists of a set of structural equations, it's possible to calculate probabilities that might first appear nonsensical. As noted earlier, the probability distribution on U, piece of U introduces a well-defined probability distribution on V, piece of V. And my cousin in England is messaging me about Meghan Markle. I'd rather read about causal inference. As such, it not only defines the probability of any single counterfactual, but also the joint probability of all conceivable counterfactuals. What's he talking about? This is actually interesting to me because while this literature is I'm very familiar with, just kind of seeing anybody try to articulate it in an intuitive way to people who are probably seeing this for the first time, it's actually interesting. I don't think he's succeeding, but I don't think it's but I don't think he's failing either. I mean, I don't think he's succeeding in the sense that I can't imagine a sociologist, even a really good mathematical one, kind of looking at this and just kind of getting it at first pass. But the explanations are pretty good and they're pretty concise. So since our model M consists of a set of structural equations, that's the other thing. Like thinking of models as a set of equations, that's also kind of pedagogically speaking, unless you had a class on linear algebra, which, unless you're unless you're in a STEM field, why would you? Anyway. Okay, it's possible to calculate probabilities that might at first seem nonsensical. As noted earlier, the probability distribution on U induces a well-defined probability distribution on V. As such, it not only justifies the probability of any singular counterfactual, but also defined. Okay, it defines the probability of any single counterfactual, but also the joint distribution of all conceivable counterfactuals. Yes. Okay. So it's just saying that we have a probability distribution on any kind of counterfactual query we might ask of this model. So, as noted earlier, these probabilities refer to the proportion of individuals in the population with specific counterfactual values that may or may not be observed. Thus, the probability of Boolean combination y sub x equals y, small y and y sub x prime equals z for variables y and z and v are two different values of x, small x, and small x prime is well defined, even though it's impossible for both these outcomes to be simultaneously observed, as x equals x and x equals x prime cannot concurrently be true. Okay, getting a bit technical here. If you are falling off from understanding here, don't worry. I mean, I think, again, we'll get to a point where once he's defined all this background, he'll understand. Well, he'll start explaining why this matters. And once we know why something matters, then we can motivate ourselves to go and kind of suss out the details later on. So to answer these causes of effect type questions, such as if x were x1 and would y be y1 for individuals for whom in fact x is what is that? X is y sub x. So this is probably a typo. This has to be x1 for individuals for whom in fact x is x small x1 and y is small y 0, right? So here was if x were x1, would y be y1, when in fact, right, that's what is happening here. So given that y equals y0, x equals x0, the way you would phrase this is like, what's the probability, given x is x0, y is y0, and x is the cause, y is the effect usually. What would y have been had x been x1? This probability, that is the proportion of the population with this combination of counterfactual values, is solidified once the structural equations of the distribution of exogenous variables u is known. In general, the probability of the counterfactual sentence, where E is any information about an individual, can be computed by the three-step process: abduction, action, prediction. So this I talk a lot about in my workshop. Abduction, action, prediction. This is where we start with the probability on U. We obtain probability of U given E. Action, replace the equations corresponding to variables and set x by the equation x equals small x. And prediction, use the modified model to compute the probability of y equals y. All right, so we start with, so we have our model. We get some evidence. That's what E here is. So E is like x equals, so here this thing here is an E. We have this probability distribution here. So think of this as a prior on U. We get this posterior on U. We change the model like thusly, and then we recompute the probability y equals y. In temporal metaphors, step 1 explains the past U in light of current evidence. Step 2 bends the course of history minimally to comply with the hypothetical antecedent, and step 3 predicts the future y based on our new understanding of the past and our newly established condition x equals x. Let's see here. So in a past paper, you get several examples illustrating the simplicity of this computation and how causes of effects type questions can be answered when the model M is known. If M is not known, But it's assumed to take a parametric form. One can use population data to estimate the parameters and subset. Great. So now we're getting machine learning, right? So if we have the full model, which we almost never do, we can just run that algorithm. So this is an algorithm: abduction, step 2, action prediction. If you want to ask, I was x equals x. I was, married to Barbara, and y equals y. I'm unhappy. Would I have been happy? What's the probability that I'd be happy if I had married x equals x prime, Susie? Right? And now we have an algorithm that can answer that question, assuming we have this model M, which we almost never do. And but if we have a parametric model, then we can train it on some data, right? We can estimate the parameters, including those that pertain to causes of individual cases. You can train this on observational data. Thus, the challenge of reasoning from group data to individual cases has been met. When the model is not known, we can prove that in general, probability of causes is not identifiable from experimental or observational data. Okay, so he's calling these kinds of counterfactual questions, these are causes of effect questions, I think. Right, because he's talking about what's the probability that x would have equals. I think so, yeah. Are not identifiable from. In general, we don't get identifiability. However, when group data and observations using group data with observations about an individual, tight bounds can be derived, which can be quite informative. We will illustrate the bounds as an example taken from a judicial context similar to the one considered by DFF. All right, so now we're great. So we've gone through the rigorous introduction. Now we want to figure out what is he trying to communicate to these sociologists he's writing to. Legal liability from experimental and non-experimental data. A lawsuit is filed against a manufacturer of drug X, charging that the drug is likely to have caused the death of Mr. A, who took the drug to relieve back pain. The manufacturer claims that the experimental data on patients with back pain shows conclusively that drug X may have only had a minor effect on death rates. However, plaintiff argues that experimental data is of little relevance to this case because it represents average effects on all patients in the study, not on patients like Mr. A, who did not participate in the study. Actually, it's interesting. Can we cast this as maybe like a modern data sciencey problem? Like you're working at Facebook, right? And you want to say you're interested in whether or not this feature caused a specific user to have a specific outcome. So the social media feed, the Facebook's, okay, fine. Usage of Facebook caused a person to go and riot at the Capitol on January 6th. And the Facebook lawyer says, no, we have plenty of people who use Facebooks and only a very small proportion of them actually went to the Capitol. And you say, and the prosecutor says, well, that represents on average, but it doesn't. That average population doesn't account for this person. Well, that's starting to feel dicey. Let's see where you go. I mean, I know where we're going with this example, but I think my example is probably falling apart. In particular, argues the plaintiff, Mr. A, is unique in that he used the drug on his own volition, unlike subjects in the experimental study who took the drug. Okay, so yeah, my example doesn't work because it's not an experiment. So it'd be like more like an A/B test. You run an A/B test and you say like, well, it looks like according to the A/B test, feature A doesn't seem to have a big effect on engagement, but you say like, well, the other person saying, well, I think A made this person engage more. I said, well, that's not what the test says. Yeah, but in your test, you were randomly assigning people to group A or B, but our user used feature A of their own volition. And here we have a whole bunch of users from a non-experimental data who, like Mr. A, chose to use the feature and were not included in the A/B test. So you, or the data science lead, has to decide, or the executive in the organization has to decide based on both experimental and non-experimental studies, whether it's more probable than not that the feature was indeed the cause of Mr. A using engaging more. Let's morph in my example. This example falls under this is actually a trick I use a lot when I'm reading these things. Is I work in industry. I'm an engineer. I lead teams and building products. I like to think of a lot of these things tend to be like these examples here tend to be life or death, either having to do with death or often with sex, and so like kind of just recasting it into a practical problem helps me kind of grab kind of grasp onto the idea a little bit more tightly. So assuming binary events with x equals x and y equals y representing treatment and outcome respectively, and we have these negations, our target quantity can be formulated directly from the English sentence. What is the probability that if x equals x, y equals y is treatment and outcome. X prime and y prime is their negation. So this x here is used the feature, engaged more. Didn't use the feature, didn't engage. What is probability that if the person had not used the feature, they would not have engaged, given that in reality they did use the feature and they did engage. And so we call that the probability of necessity. That's what PN stands for. What does he call it? So did use the feature, did engage. Probably they would not have used the feature had they not engaged. And calls it the probability of causation. Pearl calls it probability of necessity to be distinguished from other nuances of causation. Captures the but-for criterion. This is what we use. This is what they call it in law, the but-for criterion, according to which judgment in favor of plaintiffs should be made if and only if it's more probable than not that the damage would not have occurred but for the defendant's action. In contrast, PC measured. Okay. So what is this? This is probability of causation. It's a bit different. And interestingly, you'll probably talk about this. This is a lot easier to get than this. Wait. Is it though? No, I'm wrong. This is actually also tricky. If given x equals, what is this? Yeah, I've never seen actually this in the back there. So that's that y given that we did x. So that's do x, y equals y. Right. So this is what happens if there's a experiment happening. So this is the non-experiment version. This is the experimental version. So I guess what we're kind of getting at here is that we have this difference between these two things, which is this is the experimental outcome, and this is the observational kind of outcome. Housekeeping. Hello? Yeah. Okay. Yeah. Okay, no problem. Be down there. I'm on a call. I'll be down there. Thank you. Okay. Right, so this second probability is probability that they took the drug under experimental conditions and died, or they rather, in my example, that they used the feature and engaged. So they used the feature in the A/B test and engaged. It thus represents the probability that the drug was the cause of death of the subject who died in the experimental setup. Very few court cases deal with deaths under experimental circumstances. Most deal with deaths. All right. Yeah, it's interesting because it's like almost, it feels as though like, are you arguing that, is this kind of an argument that experimental results in like a clinical trial, for example, don't work, which is obviously not what we're saying. Let's see where they go with it. Very few course cases deal with deaths under experimental circumstances. Most deal with deaths. Right. So this is the argument that like you're asking, you want to know this question, but all you have is this, because we didn't. We're asking whether or not Mr. A died in normal circumstances due to the drug, not did he die in. All you're saying is as defense is that, well, we have a bunch of people who were in an experiment and they were fine. So having written a formal expression for PN equation 2, we can move on to the identification phase and ask what assumptions would. So this gets weird because you define all this notation and it's just like it kind of flies in the face of intuition, but the rigor allows you to basically write algorithms for it, and that's cool because that means that you can get robots to do it. I mean, that's what I care about it. But it always feels as though like you're formalizing something that, obviously something not killing people in an experimental setting is pretty strong evidence that it's not a harmful thing. Because the whole point of the experiment, the whole reason we run these experiments, we don't just do them for fun and then try to extend them for observational reasons. We do them because experiments generalize when observational studies don't. So, we've got some theories here. If y is monotonic relative to x, that is, if that y under this intervention, under one intervention is always greater than y under for the same subject under another intervention, then Pn is identifiable. Whenever the causal effect is identifiable, and moreover, great. So that means we have an identifiability thing here. It's like if we have for a given person, so what does that mean? Like let's say like y is engagement, right? So that means that if the feature for any given person, if the amount that they engage, given they see the feature is always more than the amount they would engage if they did not get the feature, then we can actually identify this thing. Means that we can kind of if we know the causal effect of the feature on the outcome which we would get from the experiment, then we can identify this probability necessity. We can estimate it. We can get it. And that's interesting because that means that there is no person for whom seeing the feature makes them engage less, right? So either they just have the same amount of engagement they would have had not using the features, or they engage more, but never less, right? So that means that if Facebook released some feature that's supposed to get you to spend more time on the site, there's nobody who's just like, oh man, this is stupid. I'm tired of all these gimmicks. I'm gonna use this way less. And so so that's a reason, and that might happen. That's a reasonably strong assumption. Once you maybe there's a lot of features out there where if you feel a company is trying to cajole you or manipulate you into certain behavior, you just kind of withdraw. The first term on the right-hand side of the equation 4 is the familiar excess risk ratio that epidemiologists have used as a surrogate for probability necessity in court cases. The first term here, huh? Oh, okay, I see. Okay, so he's parsed it out into things that people might be more familiar with. And it's an additive thing here, so interesting. So that parses that way, that's interesting. Although I find it particularly intuitive. The second term represents a correction needed to account for confounding bias due to probability of y given do x prime is not equal to probability of y given x prime. Or put in words, when the proportion of population for whom y equals y and x is set to x prime for everyone is not the same as the proportion of the population for whom y equals y among those observed, the value x equals x prime. Okay, so this is just a kind of correction for confounding. Anyway, I'm not really interested in the parsing. This kind of makes sense by itself. But I guess the idea is that this is something that people really kind of understand, and then this is something you might figure out from an experiment. So this you can get from data, this you can get from experiment. So that's interesting because it means that if we have monotonicity, then that counterfactual query means that you can learn this from data, observational data, and then you can learn this through experimental data. Equation 4 thus provides a more refined measure of causation which can be used for monotonic whenever the causal effect can be estimated either from randomized trials or graph-assisted observational studies. So I guess if we're going back to our example here, we're like, okay, so this thing we can learn from people like Mr. A, and then this is the information we get from the clinical trial or from the A/B test. More significantly, it has been shown that the expression in 3 provides a lower bound. What expression? Why? Interesting. So we have a lower bound here, but isn't that Pn equals P of y given do x prime over P of xy? So we have some kind of tight lower bound here. I'm trying to understand why this is significant. I've seen this before, but within the context of this discussion here, it'd be nice if you can get a lower bound that only required observational data, but this is the do here is implying, unless you're doing some kind of unless you have conditions for adjusting for confounders here, that you would need experimental data to construct this bound. But we up here already said that we can get this, we can actually solve for this from experimental data. So this would be more interesting if we were only doing this for observational data, if the bounds were defined in terms of observational data. Let's read on. In other words, I'm having trouble understanding why 5 is useful within the context of this conversation. In drug-related litigation, it is not uncommon to obtain data from both experimental and observational studies. The former is usually available by the manufacturer or agency that approved the drug for distribution, while the latter is easier to obtain by random surveys. If it is the case that the population and survey data have been drawn at random from the same population, then the experimental data can be used to estimate the counterfactual of interest. For example, probability that y under an intervention x is equal to small y for the observational and experimental sample populations. In such cases, the standard lower bound used by epidemiologists to establish legal responsibility, the ERR, can be improved substantially using the correction term of equation 4. Oh, so this is the lower bound. I wonder if he's got a typo here. Because he said this is that lower bound doesn't make much sense to me. I think that lower bound is a typo. I could go look it up, but I'm not. Let's just look it up. I have the book on PDF somewhere here, I think. To find this counterfactual probability of necessity. To monotonicity. Aha. Yep, typo. Okay. So there's no do here. Pre of y given x. Y given x prime over y given x. You've got pre of y. Interesting. So it looks like this is the first. This is the lower. The max of this is the lower bound, and which is our ERR. And the min of this, well, I didn't know, or is it the same? So I think this might be the same as here. No, it's not. It's different. might be. So it's a bit, this I'm pretty sure this is wrong. I'm not sure what's going on here, but anyway. Long story short, we got some bounds on it. Can be used to exonerate drug makers from legal responsibility. So why is that? So standard lower bound. So we can use the lower bound. Why does the lower bound give us the ability to establish responsibility or exonerate? We're talking about that removing the, so in this case with the drug, that we don't, given that they took the drug and they died, it's probability that they wouldn't have died had they not taken the drug. And so we're going to bound that. And so if we have a lower bound on that probability, then you can say like, well, I have a lower bound here, so the probability is at least this high. And if you have an upper bound, you can say, yeah, I have an upper bound here, like the probability is not, could not be higher than this. I see. Interesting. I never thought of it like that. So that would be interesting from a machine learning agent modeling perspective, because I'd say I'm the agent trying to reason about what action, say several steps ago, led to my current reward outcome. And I'd say, well, the probability that that action is responsible for this bad reward is at most this high. And the probability that the action did not cause this back, did not, you know, if I'm thinking like, well, what's the probability that this action had nothing to do with it, then I could say probability the action is this impact would never exceed this number. We can't exceed this number, so you know, if I put like a significance threshold on that. Okay, interesting. Numerical example, I'm going to not work through that. We have a table there, it's gonna work. Let's look at let's continue with the arguments here. With 6 minutes left. To see how informative the bounds are and how sensitive they are to variations in the experimental observational data, consider the following example. Assume that the population of patients contains a fraction R of individuals who suffer from certain death-causing syndrome Z. Simultaneously makes it uncomfortable for them to take the drug. Referring to figure 1, Z equals Z1 and Z equals Z0. All right, let's try again with the feature example. I just get super lazy when it comes to reading about patients. I just assume that the population of patients contains a fraction R of the individuals who suffer. So there's some kind of syndrome that makes some people, let's say this is using the feature or not using the feature. Some people have some kind of predisposition that makes them not want to use the feature, and will also affect how much they engage. So people who have this profile will be less likely to use the feature, and maybe more or less likely than other groups other people to engage in the website. Okay. So assume that patients who have this profile will not engage. So like the probability that they won't engage if they have this special profile is 1, regardless of whether or not we introduce the feature. Patients who don't have this special profile will engage with a probability of P2 if they see the feature, and a probability of P2. Probability P1 if they see the feature, and probability P2 if they don't see the feature. We will further assume that the probability P2 is greater than P1. So in other words, probability of engaging given the features is greater than the probability of engaging if we don't see the feature. So that the drug appears to kind of be, well, I guess risk factor. All right, so what we're doing is we're constructing kind of joint model here. So what do? We kind of adjust for Z. We get the joint distribution, sub in some parameters, and we get this full joint. We calculate this probability of necessity based on, I map it against this Q2. What is Q? Q is not. So okay, so we have some function here. Lower bound of probability of necessity. So we have, okay, so we're basically visualizing the lower bound. Okay, so we just did a visualization of these bounds. So great. So let's see. This looks like maybe all right. Kind of wrapping it up here. Is guilty with probability whenever possible. People tend to disbelieve this possibility for 2 puzzling aspects of the problem. That a hypothetical, generally untestable quantity can be ascertained with probability under certain conditions. That a property of an untested individual can be assigned a probability 1 based on the data taken from sampled population. The first principle. All right. So this is just kind of addressing what people don't believe, right? Number 1, people don't want to believe that I have this thing, this probability of necessity is, I can't test that, right? I can't just go in, because we're talking about like X happened, what would have happened had X not happened. We can't have X happen and X not happen at the same time. So we're saying that most people have, like, it's unbelievable that you can estimate this thing, this probability of necessity, if we don't have, if we can't even validate it. And so the argument here is that, yeah, once we give something some formal semantics, we essentially define its relation to the data, and it's not inconceivable that data obtained under certain conditions would sufficiently constrain that quantity to a point where it can be determined exactly. Number 2, what's the second puzzle? Probability of an untested individual can be assigned a probability. The property of an untested individual can be assigned a probability 1 based on data taken from sample population. So this is the idea that we're getting some data from a sample population, and then for a given individual, we get some kind of 100% probability, which tends to be very, in statistics, you take a sample, you get 100% of anything, you start to get suspicious. So the second puzzle is one that gives most people a shock of disbelief. For a statistician in particular, it is a rare case to be able to say anything certain about a specific individual who is not tested directly. This emanates from 2 factors. First, statisticians normally deal with finite samples, the variability of which rules out certainty in any claim, not merely about an individual but also about any property of the underlying distribution. This factor, however, should not enter into our discussion, for we have been assuming infinite samples throughout. Right, so we're just saying that we're assuming we get infinite samples. We know these probability distributions fully. Once we start estimating these distributions from data, we'll add some uncertainty, but that's fine. Even if we know the distribution precisely, we cannot assign a definite probabilistic estimate to a property of a specific individual drawn from that distribution. The reason is so the argument goes that we never know let alone measure all the anatomical and psychological variables that determines the individual's behavior, and even if we knew, we would not be able to represent them in the crude categories provided by the distribution at hand. Thus, because of this inherent crudeness, the sentence "Mr. A would be dead" can never be assigned probability 1. Right, so he's saying that like people are complex, and so just saying like A would have, sentence "Mr. A would not have died" or A would have died given different conditions. There's just too much going on for us to be like 100% true. He would have died. This argument, advanced by Friedman and Stark, is incompatible with the way probability statements are used in ordinary discourse, for it implies that every probability statement about an individual must be a statement about a restricted subpopulation that shares all the individual's characteristics. Taken to extreme, such restrictive interpretation would insist on characterizing the plaintiff to minute detail and would reduce the but-for probability to 0 or 1 when all relevant details are accounted for. It is inconceivable that this interpretation underlies the intent of judicial standards. By using the wording "more probable than not," all right. So he's just kind of arguing that unfortunately, we kind of make probable statements about people all the time without knowing, what they wrote in their diary when they were 3 or something like that. So, when they wrote in the diary when they were 8. By using the wording "more probable than not," lawmakers have instructed us to ignore specific features that are either irrelevant or for which the data is not likely to be available, and to base our determination on the most specific yet essential features for which the data are expected to be available. In our example, the 2 properties of Mr. A are noted: that he died and that he chose to use the drug. These are essential and were properly taken into account in bounding probability necessity. In certain court cases, additional characteristics of Mr. A would be deemed essential. For example, it is quite reasonable that, in the case of Mr. A, the court may deem his medical record to be essential, in which case the analysis should proceed by restricting the reference class to subjects with medical history similar to that of Mr. A. However, having satisfied such requirements, and knowing in presence that we will never be able to match all the idiosyncratic properties of Mr. A, the lawmaker's intent must be interpreted relative to the probability bounds provided by the probability necessity. Great. So this is really just kind of summing this up. Well, he has a summation. Let's just look at that again. So again, there are parsing effects of causes and causes of effects is right, and that it kind of separates group data and individual data. However, we got some math that ties these 2 things together. And that they should reap the benefits unleashed by this theory. Yeah. Pearl knows how to do his own horn. Give him that. Great. So this is just like the use of probability of necessity to talk about but-for causation in a legal setting, with hopefully kind of clear applications to data science and artificial intelligence. Well, I hope that I made some of those clear. Thanks for signing on. We'll be reading this in the probabilistic. So this is a reading group we have on Mondays at 3 p.m. Eastern Time. where we're looking at basically kind of the connections between probabilistic programming and causal inference, causal models. So this is what we're talking. So this will be read next Monday. Let's see, that's today's the 9th, so that'll be 6 days from now, so 15th. And at 3 p.m. Eastern time. Hope to see you there. If you do join, well, you should read the papers, but now you've at least read this with me, so hopefully you'll be ready to go when we do this. I hope to see you there. Thank you.